last part of the strained silicon story, in which we take a temporary deviation just to explain the supply chain, technology chain. We've used this terminology in this class so far and have talked about vertical and horizontal aspects of this chain, but I just wanted to spend a little bit of time just talking about the generic nature of such a supply chain in any industry, whether it's software, medical, or semiconductor, or what have you. And the way to think about this is that there's a flow of goods or information, whatever the valuable thing that is moving, the embodiment of the innovation needs to get to the market, which we've labeled here as customer, in some particular fashion. So here, you can think about the customers at the end of this. So this would be, the marketplace, because they've purchased something, and that's where the innovation ends up. Now, practically speaking, to get there, it has to go through something. So, for example, in general, many things, physical things, go through the following. You have some sort of material. I mean, it could even be an ore, or, something like that. In this case, it could be a finished material, right? Something like a silicon wafer, or, silicon itself, metallurgical grade silicon could be the, a chain further down from there. So there's all this process where you add value as you move up through the supply chain and technology chain. So those materials could be used in devices, and then the device is used in some sort of bigger box which has other devices in it, and then there's some sort of distribution, and then there's finally the end customer. And this could be business to business, it could be a real separate consumer, but the general idea is there's some sort of way in which the innovation is created and absorbed into the marketplace, and we're generally calling that here like sort of the flow of goods and information. So some examples, if you had, and again, there's many sub-levels in here that we're not showing, because even in distribution there could be several levels, and even in the box, Apple, when they make their iPhone, it goes all over the place. So I'm just simplifying this to say that any time you're doing any innovation, iteration eventually comes into play, and actually, obviously an implementation in its broadest form should be occurring at the beginning, even when you're doing research, even though this could change while you're doing the research. If you're doing something further on time, you should still understand how this is today and how it might change depending on your success. So, give the example here in semiconductors in purple, where you have metallurgical grade silicon, which is made into silicon wafers, and then, as we've mentioned before, chip. And then you've got, all these other technologies that end up going in. You end up with inside a box, and it gets distributed, and in this case, person. But to give you another idea of how it's different depending on the technology and the supply chain, at the very bottom materials, for pharma, you have polymers and drug, and these things are very basic, important things, and can have very important intellectual property. Here, that's true down at the material level, but you're adding a lot of value all the way through. In this case, really the fundamental value is way down here, and then the pill's a pretty simple product. It's not a complex product like the information age stuff. In the sense that it's a pill, and then really gets complicated again at the distribution level, because you have the pharma company itself, you've got doctors, hospitals, so, and then finally the customer, right, the patient in this case, right, is the ultimate. And then of course there's a whole nother thing in that while you're developing it, there's additional things that show up here that don't show up over here. So, for example, the FDA will be here for a while, but then disappear when finally goes to market. So, anyway, every single thing that ends up in the marketplace, even if these things are virtual, you still have to have some way of moving them to the marketplace. Now, in semiconductors, I've mentioned this before, but just to make sure everybody's clear on this, to show the strained silicon example, the vertically integrated companies initially existed because nobody knew how to make the best silicon crystal, and that was considered to be a very proprietary thing. And so initially people concentrated on all this in one company. They all depended on each other, and so you have a lot of innovation because everybody's together in the same place, and there's limited knowledge, and if you can get the right people together with the right investments and everything, you can actually have much success. And then once silicon really took off, you have 20 of these companies, right? 20, 40, 50, 60. And so what happens is with so many companies vertically integrated, and I saw this process happen actually in 3.5 materials while I was at Bell Labs, eventually somebody figures out, well, if there's 20 of these companies, I can take, and I described this before earlier in another lecture, I can supply all this material. I can supply this material to all of them, all 20, and my volume would be higher, and so my cost will be lower than just one company because they only take so much of that volume. Where if I aggregate the demand from all 20 and I make a bigger factory, I can actually beat them, and then they'd have to buy from me. And of course, that's why generally this process starts from the bottom up, where initially somebody says, aha, we'll disaggregate the material, and then the people do processing and ship are still integrated. But then we talked about the TSMC example. That's when we talked about this before. And then that becomes disaggregated, and then you have the fabless chip company finally, right? Well, one of the most important things to recognize in the strained silicon, and it's still true today, by the way, the things I'm doing today are still related to this because most of the industry is like this. If you're not disaggregated, you have to have an unusual implementation. And there's two companies that have so far stayed vertical that are pretty well known in the United States, which is IBM and Intel. IBM is interesting because their business model has nothing to do really with, well, it doesn't, the business model isn't directly related to microelectronics, it's related to services, and that microelectronics gives it value, and so they're willing to support this activity and keep it together. Of course, the material is still outsourced in the sense that for silicon, we buy wafers, that's still done, but the process and chip are still together inside IBM. And of course, Intel, same thing, process and chip level are together inside Intel. And that's because they basically have market domination in PC microprocessors. As we know, they don't have domination anymore in new markets like the smartphones, but they still have domination in that, and that's allowed them to keep them integrated. But in general, there's a trend. If you have full market competition in a lot of those segments, there, most everybody else has disaggregated into this kind of model. And what that meant for Amberwave and strained silicon was that we pretty much realized that what we needed to do was to have vertical information in our company, because otherwise the full advantage of strained silicon could never be seen. And we saw that in many ways. For example, when we went to materials people, they actually no longer knew what was going on in the process, and especially the chip level, like what people might want to have to do in the middle at the top end. They had no idea about circuits, and they certainly didn't have any idea about device evolution. Because, don't forget, that's not because they're ignorant or anything, it's because that the expertise they put in there was to go horizontal, which meant all of the innovation was applied to higher volumes of things, retaining the quality or improving the quality and having very high volumes. How do you do that and keep costs low and drop costs, right? And so the innovation went in a different direction here. And the reason, by the way, that we're seeing this is that we had to figure out how to make strained silicon, because at this time we're working this infrastructure, not the vertical one. And so we needed outside materials people to make the silicon germanium silicon structures, for example. And then we had to pass that into a fabrication facility, whether it's like a AMD, which is vertically integrated at the time, which ended up being our partner, or it could be, so AMD had both process and chip, but of course since then they've disaggregated. Again, the same forces, they're not a dominant market player, so they had to separate. But most of the players, like UMC became a partner. They're a foundry. They're TSMC competition. They're much smaller. And so what became clear is that, well, if we want to drive this thing, we have to teach these people how valuable it is. So what this means is that you don't have to look too far and to say that, well, Amberwave would have to have the expertise to be vertically integrated, and we don't need to have designers. First of all, it's impossible because it's kind of expensive to have everything in one company, especially a small company. So, but you could certainly say we can get up to the device level, and then with somebody like UMC, or in the case of AMD where they have their own designers, they can see the advantage. And so that's what we meant here by, new products ultimately, when you're in horizontal, have to come from some entity, whether it's a big entity or it's a small entity. Somebody has to have this vertical knowledge in order to let these pieces affect each other again, so that new things can pop out. And actually, when Amberwave started in the wireless and opto space, we wanted to use fabs to produce new products that didn't depend on Moore's law. But of course, the thing that really took off was that at the time, at 90 nanometers, Moore's law had ended. Now, this wasn't public knowledge, but most of the advanced places like AMD and Intel and all that had already made 90 nanometers and saw that the current wasn't high enough. So where we wanted to build innovation and create new, drastically different things using the same fab, people still just said, well, if I got this problem, I just want to use it to make my regular MOSFETs better, and with that extra boost I'm getting, that'll allow me to continue on Moore's law. So again, another shift where we had been looking at applications that were to use the same fabrication facilities and do something drastically new at the product space, but in fact it was pulled in and used for Moore's law. At external supply chain, why we're ramping this, remember I was saying this over here, we had to use somehow we had to have material, and it had to go in, and we had to help the companies process stuff, right? So what we did was we had to find initially smaller manufacturers, so more boutique. And we did. And what's amazing is with those partners, we're able to make the following. These materials, coming in from the outside, because the fabs didn't have the facilities required to make these materials. Only the material suppliers did. So we were able to work with them to make this incredibly precise 20% silicon germanium substrate on silicon, as you can see over here. And it had 175 angstroms, in other words, 17.5 nanometers of strained silicon. And we had to keep the defect density down to in the 1 times 10 to the 5th range, like closer to 1 times 10, not 9 times 10 to the 5th. And amazingly enough, by working with our partners, at the beginning, this is the usual thing. You just say, yes, we're going to do that. But we were able to accomplish this. Not only that is that we had used the physics of understanding where the strain came from to actually get rid of the surface roughness. So for many, many years, people were trying to figure out how the heck we had these materials with no surface roughness. You can see here what we were able to accomplish, again, with separate outsourced CMP work. And again, this is one of the huge advantages. We did not have to build a lot of infrastructure once we had those relationships, but we had, if you look at the RMS roughness, typically those strained silicon materials had 20 to 100 angstroms roughness, which actually doesn't affect it too much, but it affects the tools in the fab and things like that. And so eventually, because we knew that these things were a residue from previous strain fields, what we realized, if we left the top layer a little bit thicker before we put the strain channel on, we could do a chemical mechanical polish. And you can see here that our wafers, when we ended up shipping the customers, like I said, for years they were wondering how we did this. We'd have less than 2 angstroms roughness. For those of you remember, the Bohr radius for an atom is 0.5. So these are basically atomically flat materials, which is what people expect from silicon. And this was great intellectual property because it was very difficult to change. And we were able to ship many wafers to different manufacturers to get them started on our technology. And we could show them how to make devices from it in their fab. So things are looking pretty good at this point. We have, this material figured out. These really precise strain layers on top, and with 6 people in the company, actually, we signed a deal with AMD. It's very exciting, and we have to get those criterion that I talked about somehow from working with external manufacturers, and we did. You can see here we're very excited about the fact that we're finally getting to a stage where we could get something into real manufacturing hands. So this is really when the company started to take off. And we ended up working with most major manufacturers around the world except for Intel. Just some personalities here. This is Ken. He was our main person in charge of making sure wafers flowed through different processes, operations person, really. Meg Bolsaro was my first grad student and co-founder of the company. And this is my father, who had retired, and Meg and I were very busy with working with market application, sales, and technology, and everything else. And he was, for many years, doing many different things, and we could count on him for making sure that the employees had health insurance and all of the other nasty things that typically we didn't have experience with at the time. This is myself, and this is our first CEO, Mark. He was the first CEO that, once we had seed funding from venture capitalists, we were able to hire him in so that we could start defining traditional roles in the company. So at this point, what's happening is we have amber-wave strained silicon. Everything is pretty much defined now. We even know the thicknesses. We know this and that, and we have these companies popping these things out for us. We're clearly going for digital CMOS. AMD is the one who stepped up and said, we'll do it. Then we have UMC, and we have actually a whole list of other ones that are trying it. What are they trying? They're buying engineering services from us. They're buying materials from us. We told them that IP would be down the road because we have licenses on all sorts of strained silicon, because something I'll talk about separately in IP lecture. We actually built a vertical patent portfolio. So like that supply chain we just showed you, we had figured out that since we are doing the technology from materials all the way up to simple circuit, we should also patent that way to fully protect ourselves. And so we have a very strong IP portfolio that we knew people would have to license when they finally go to market. So we're kind of vertically integrated in knowledge, but we're fab light in the sense that we have a small research fab, but we don't make our own wafers. We understood the supply chain, and we had these 2 initial real customers. We worked with others, but they're the ones that really want to go forward with it. Now the world changed because and I removed the implementation, because that implementation, we had revenue, we had everything, changed because we could grow with that model. In other words, when we get engineering services, you get materials, you can actually grow the company, you get revenue, you get profit, you can feed that back in, you can do more financing. But the big change was that Intel announced in 2002, that didn't change as much as like by 2004 when they started manufacturing. That really changed the game because they were not one of our partners. And what they did was, instead of having outsourced material stuff, they actually implemented epitaxy directly into their fab. Now, of course, only someone with the resources like Intel could do so. But it didn't matter because, in general, the rest of the industry is kind of a follower. And so what happens is they froze, and then we had tough decisions to make. So the way I represented that here is uncertainty was reintroduced into implementation, right? Remember, this was narrowed down, but now it gets opened up again. It's like, okay, for Amber Wave then, now that Intel's doing this and everybody else is watching, and all of a sudden the sort of implementation of the industry for strained silicon, when a player like Intel does it a certain way, everybody freezes. And so this became, but it doesn't take you, it became a real problem for Amber Wave, the company. Of course, it's great for the technology in the sense that it's going to be implemented. So the technology side of someone like myself who wants to see innovation reach the marketplace, it's very clear it's going to reach the marketplace. But now for the company, the question becomes, what's its role? And so from a company perspective, the implementation is pretty clear. It's going to go to two choices. You're going to have to build your own product, or you're going to license the technology now. You're not going to actually do the steps yourself. And to give you an example of how this is going to be the case and why it's kind of obvious, is that I think at the time we were making enough 200 millimeter wafers so that we could feed, I think, a fraction of even one commercial 200 millimeter fabrication facility. And so you're talking about people implementing this around the world all at once, and there's no way that we're going to be able to supply them, or our medium-sized suppliers by now, they're not going to be able to supply them. So it's pretty clear we're going to have to either license the technology. Now, we built that nice vertical portfolio, or we're going to have to build your own product. That is, go vertical and use your partners to actually use our foundry like UMC to build your own final integrated circuits in some area that's obviously not a microprocessor, because that'd be vital, right? So this is where actually, when a company has to make a decision like this and you have a full board and lots of investment, there's a bit of a struggle. And even though I saw this early, it took a little bit for the rest of the company, the board in particular, to see it. But eventually, through circumstance, actually, they came around, because eventually the company, usually for a small company, if someone commercializes your technology, then you pretty much have to become a licensing company. And so even though there was some resistance, eventually Amber Wave did become that. And eventually, after much process, Intel licensed Amber Wave strained silicon technology, and kept on incorporating different versions of the technology as time went on. And today, we finally went back to the original vision, where we have projects working on integrating 3.5s and CMOS into the same integrated circuit in the silicon infrastructure. And in 2013 anyway, we're starting those efforts, and we hope that in a few years, first prototypes of finally taking that original lattice mismatched technology and having it appear in various end applications, including monolithic 3.5 CMOS products. Now, you can see here that intellectual property at the end of the day was key for Amber Wave. And so in the next lectures, what we want to do is talk about intellectual property. And I want to make sure that everyone understands that this is not because intellectual property is the most or only important thing. it is just one more component in the implementation space, but it can be an important component, and so we want to talk about that. So this is the end of lecture 12, and we'll begin with intellectual property. Lecture 13.